Hello, my name is Kyla Jean. Today I'm going to be presenting to you how calculus relates to my major, which is natural science with a physical focus. Now, obviously, I am no expert by any means. However, I'm just drawing topics of interest that have related to the prerequisite classes I have taken and the application within them. Now, obviously, natural science is a branch of science, but natural science deals more with the natural, physical aspects of science. To be fully honest, it is difficult to pinpoint natural science to a singular area of study, so therefore I've listed a few classes, both life and physical science, that I have taken as prerequisites thus far that have relation to calculus. Because I am graduating this semester, it was definitely easier for me to make this list because I've already taken these courses. It is completely impossible to have a proper understanding of the natural science classes without calculus. This is because natural science uses evidence from experimentation and observation empirically and numerically. Calculus can be used as a tool to easily organize these findings and make it an easier and quicker process for everyone involved. In the next slides, I'm going to dive deeper into why I chose these example courses, and I'm also going to be giving practical application examples, meaning nothing too radical or unrealistic. It should come as no surprise to most that calculus relates to physics. After all, that's why it was invented in the first place, wasn't it? When I look back to the first physics course I took, I can relate Calculus 1 most to the description of motion. The very first thing I can recall learning about in my physics course was a vector, and that's an object that has both a magnitude and a direction, and we learned a lot about that in section 2.4. For example, we started off learning about average velocity, which is displacement over the elapsed amount of time. And in physics, velocity is considered the first derivative of position with respect to time. And this repeats over and over, with acceleration being the second derivative and jerk being the third. I can relate a lot of the problems that we did in this section to a lot of the physics problems that you witness in the first half of the class, where you are negligent to air resistant and you're calculating, for example, when a ball is dropped off a deck or a ball is dropped off a building or someone's jumping. You're just calculating velocity or how long it took for something to hit the ground. Physics is extremely concerned with change, and that's why calculus is so important, is because even for the most simplest problems in physics, you will end up needing a calculus equation or at least a calculus concept. For example, the very first physics lab we ever did was having to do with harmonic resonance. Harmonic resonance has everything to do with the fundaments of Calculus 1 concepts, such as limits and, for example, summation, like we just learned. It makes it easier because it helps you how to understand divergence and how it occurs in the series that follows. Another thing that's introduced later in the course are kinematic equations, which are ways to describe motion, whether that be a point, a body, or a system, without considering the forces that are acting upon it. And just to really drive this point home, you can pick any kinematic equation and easily replace the variables within that equation with derivative formulas. So, for example, it wouldn't matter if you wrote velocity or the first derivative of position with respect to time in an equation. It's the same thing. An application of life science to calculus that I can think of is ecology, which is a course I'm in currently, and biology. For example, right now in ecology, we're learning a lot about population growth, which can be measured as a rate of time, essentially giving us a derivative. This can also therefore be applied to competition dynamics, which we're also learning about, which is where individuals of either the same species or different species compete for a certain position, a certain resource, or a certain space. The same concept of a derivative can also be applied to measure environmental impacts over time, whether this be a natural disaster, which, for example, could be like an earthquake or a hurricane or a flood, and it can also be used to, unfortunately, measure man-made disasters such as war, toxic spillage, and pollution. From a biological standpoint, Calculus 1 concepts are extremely valuable. For example, limits can be used to understand boundaries and create constraints on growth and evolutionary rates in the human population. Another really relevant example I can think of off the top of my head is during the pandemic. When COVID was on the rise in the United States, you could readily pull up a graph that showed you how the transmission rates varied in your county and how they were projected to trend in the future, and it's all thanks to derivatives and calculus. Concepts from Calculus 1 can be seen time and time again in chemistry and in organic biochem. I have taken chemistry the most out of all of the sciences in my Napa Valley College experience, and I can say for certain that I see calculus the most in physics and in chemistry. Going back in time to my very first chemistry lab that I ever had at Napa Valley College, I recall that we learned how quickly a reaction can change with respect to the concentration of certain reactants and how the reaction changes over a certain period of time, which is essentially a derivative. We can, for example, use the concept of determining maximum and minimum values for a system's energy. This can help us because we can see its local trends, where it peaked and dipped, and determine what that means for the experiment at hand. We can also use Calculus 1 for reaction kinetics, where we use an instantaneous rate of a chemical reaction during a specific point in time to see how it's trending there. Entropy is also another significant example I wanted to pinpoint on the slide because entropy is the measure of disorder expressed in a system, and it represents the cumulative change, which is often expressed in integrals. Wave functions, for example light, which is both a particle and a wave, sound, and color can be predicted for their probability to appear in a specific region because of integrals. This is because integrals can not only be used to find the area or volume underneath the curve, they can also help us with the generalization of trends within a graph. Another topic I'd like to bring into this conversation is the topic of equilibrium, where opposing forces are in a state of physical balance. Limits can also be applied to the very first experiment we ever did in chemistry, which was titration, where you're trying to get closer and closer and closer to a certain point, which is eventually neutralization, but you aren't going too far over and you aren't straying too far under. Generally, calculus relates to a lot of different concepts, but it mainly relates to thermodynamics and kinetics. As you may notice, in the previous slides I didn't mention what I had originally listed in the prerequisite list, which was algebra. This is because although it was a prerequisite, algebra is actually the foundation for calculus, not the other way around. So, as you can see, calculus is valuable for not only its classical mechanics application, but also optics. It plays a crucial role in thermodynamics, which I dove deep into during my Chemistry 2 and Organic Chemistry journey. Calculus is probably one of the most practical and useful applications of mathematics we see in the field of natural sciences today, because of its diversity across different fields. Calculus aids in explaining continuous change and instantaneous change and the complex nature of the natural science world. By understanding a lot of the key concepts we've learned in Calculus 1, we can analyze and predict a wide range of natural phenomena that come up in a lot of natural science classes. Calculus can help with the explanation of different kinds of data and their collection, as well as to help make prediction based on current outlooks. Just from taking this course alone, we now know the basic definitions, notations, and theorems, and we will be able to apply mathematical techniques more appropriately in the future. We now recognize the power of math, and it models real-life situations. We are able to critically assess and explain mathematical arguments more realistically. As you can see, There is a wide range of calculus implementation in all physical and life science courses that help sort and categorize everything in a more efficient manner.